Part B. A 0.057 kilogram tennis ball is dropped from rest, a height of 1.3 meters above a bathroom scale. It bounces off the scale and returns to a final height of 1.1 meters before stopping again. The scale measures the upward normal force on the tennis ball in newtons as shown in the plot. So this is during the collision. So before the collision there's 0 newtons. During the collision the force goes up for a while to a maximum of 36 newtons, then it drops back down to 0, and after the collision it's 0 again. Question is, what is delta t, the length of the collision, while the tennis ball is in contact with the scale? So there are 3 segments to the motion. It's going to be the fall, the collision, and the rise. So I'm going to call these segments 1 and 2 and 3. So segment 1, you've got V initial equals 0, and the gravity is equal to the acceleration in the y direction, or acceleration in the y direction is negative the gravity. So V final squared equals V initial squared plus 2 times a sub y times the y. Now we know that it falls a distance of y equals negative 1.3 meters. Okay, so and then V initial equals 0, so this goes to 0, so V final is equal to the square root of 2 times negative 9.8 times negative 1.3. The final speed there is equal to 5.048 meters per second. Now that becomes the initial speed, so final for segment 1 becomes initial for segment 2, right? During the collision. So V initial for the collision is 5.048 meters per second down. We know that this was down. Square root actually has a plus or minus sign in front of it, so this is actually, we know that this is negative. Because we know it's accelerating downwards. I want to now skip to segment 3. We have its V initial is unknown. This is after the bounce. It's going to go upwards, but it's positive. So we don't know what its value is, but we know it's positive. We know that y is going to be 1.1 meters. That's how far it goes upwards. Let me draw a line here. And V final is equal to 0. So again, we're going to use the same equation. V final squared equals V initial squared plus 2 times a sub y, which is negative 9.8 times y. This one goes to 0. So we have V initial equals V initial squared equals negative 2a sub y times y. So that means that V sub I equals the square root of negative 2 times negative 9.8 times the 1.1 meters. This one turns out to be 4.643 meters per second, and that's in the upward direction. Okay, and the initial for segment 3 was the final for segment 2. Make sense? So that means that the V final right after the collision is equal to 4.643 meters per second upwards. See what I'm getting at here? I want to see the change in momentum during the collision. So the delta P, so the collision, let's now look at, which is segment 2. Delta, it's supposed to be delta, let's actually make that a little easier to see. Let me grab my eraser. Delta P equals m times delta V, because m is a constant, is equal to the mass of the tennis ball, which is 0.057 kilograms, times the final velocity, which is 4.643, minus negative, the initial velocity was 5.048. Okay? And these are all meters per second. So delta P, plugging that into my calculator, I get plus 0.5524 kilograms meters per second, sometimes called the Harlow unit in class. And we know that the area of a triangle is 1/2 base times height. Okay, so it's equal to 1/2 times the F max, which was 36 newtons, times delta T. So the impulse momentum theorem is that delta P equals this impulse J. So that equals F max times delta T divided by 2. So delta T is equal to 2 delta P divided by F max equals to 2 times 0.5524 divided by 36 newtons. So I got 0.0306 seconds. So to two significant digits, I've got 0.031, and don't forget the units, seconds.